Would you call it lovely?
Yeah,
I sure would.
it's a nice day.
What about you, Texie? Okay. All right, here we go. Would you, you won't need notes here. We're just going to do some of the homework together. So I'm going to review some things, knock a few out the homework together at the same time, kill two birds with one stone. And I thought I'd turn this on, but I did. So the idea is using the derivative in various ways. We don't just take derivatives and call it good. We use the derivative to find extreme function. So that's the start of the show. Would you, let's actually go with the hierarchy. First, you start by learning critical numbers. What are critical numbers? Critical numbers are, oh, okay, so place holes and stuff like that. Critical numbers where, does the derivative have to exist at a critical number? Okay, well, let's go through it here. Actually, after we talk about critical numbers, we're talking about using the critical numbers. Let's start with critical numbers because it sounds like we're a little rusty. Critical numbers, or critical points, different textbooks use points, different textbooks use numbers. Either one, they're the same. So if you say critical points and I say critical numbers, that's fine. Critical numbers are values in the domain of the function, that's important, where the derivative is 0 or does not exist. They are candidates for interesting things happening. Go to box 1 on the homework, please. Box 1. The question says, find the critical numbers of g of t. Let's start with the domain so we don't give an answer that's dumb, that's not even on the curve. What is the domain? T must be 4 or less than or equal to 4. I remind you, you can use interval notation, that's fine too. When we go to take yield derivative here, g prime, what derivative rules will we need to employ? Product rule, and because the second is a function within a function, we'll also have to use the chain rule. It's actually a couple functions within a function. So, would you take that derivative and then start doing a little algebra cleanup to find the critical numbers? How are we doing, people? Okay, are we done? All right. So first of all, check your derivative. Do you agree something like the derivative of the first times the second is root 4 minus t? The derivative of the 4 minus t needs to be done carefully. I got something like 1/2 4 minus t to the negative 1/2 times the inside derivative of negative t, which is negative 1. Yes? I took a cleanup step and rewrote that big mess to something like that. Now, there are typically two different approaches algebraically from there. Some are taught or in the habit of clearing the fractions, which is to say multiplying through by 2 root 4 minus t. I'll leave the jury out whether that's bad or not, but if you do that, you get 0 times 2 times 4 minus 2 minus t, and t equals 8/3. So what's wrong with that? Well, in doing so, they just lost one of their critical numbers. Okay, I feel like that's risky stuff. I feel like it's better math to get a common denominator, and it's just about the same amount of work. 8 minus 3t over 2 root 4 minus t. I personally think this is better because then your critical numbers are both presented. G prime is 0 at, where is G prime 0? At t equal 8/3. G prime is undefined. Remember, critical numbers are where the derivative is 0 or does not exist. G prime is 0 or is undefined at t equal 4. Are those both in the domain of the function? They are. And so those are the two critical numbers. Okay? Questions? All right. After you found critical numbers, then the question is, all right, so I have these places where the derivative is 0 or doesn't exist. So critical numbers could be derivative is 0 because there's a max. Could be the derivative is 0 because there's a min. Or it could be derivative is 0 because there's more of a saddle point kind of thing. Likewise, critical numbers that are D and E could be a min. They could be not a min. Could be a lot of things. It's probably not discontinuity because of the domain thing. So critical numbers are candidates for cool stuff, but not guaranteed cool stuff. So the second typical question, and you learn in the calc book, you would usually call this chapter 3.2. 3.1, 3 is derivatives, 3.1 is critical number, 3.2 is first derivative test, right? What's cool about these critical numbers? F equals C is a critical point of F. If X equals C is a critical point of F, and F prime changes from positive to negative at X equals C, then F of C is a local, what? Max. All right, now, this is going to be a little bit of difference between me and Ms. Cannon in some problems. When you state the first derivative test, I don't want to hear F changes slope from positive to negative. Now that's true, and it definitely makes a max, but I'm a math theory guy, and it's not called the F-slope test. I've never seen in a textbook the F-slope test. It's the first derivative test, and your answer and your evidence is the first derivative, not the slope of F, the sign of the first derivative. So it's not F changes slope from positive to negative, it's F prime changes sign from positive to negative. Understood? Okay. X equals C is a critical point of F, and F prime changes negative to positive. It indicates a local. Now, to see if you recall that, would you go to box 8 on the homework and do that bad boy, please? Find, I'm going to give this a little clarification. This words doesn't read carefully. On the AP test, they're very particular. I'll read it more like that. Find the X of all. In other words, find where the relative extrema are, not what the relative extrema. Okay? Obviously, you should have a clue what the shape of this graph looks like, so you kind of know the lesser will be a max and the greater x will be a min. But do the sign test for the practice. Ready? Okay. Your conclusion in -2, what is it? F has a local max at x equal 2 because F prime changes from positive to negative. I am fine if you write little positive sign, little negative sign. You can write the word positive to negative. I'm getting the impression that I'm not as big a stickler about abbreviation as Ms. Cannon. I don't care if you write B, C for because, where I was told she does. I will freak out though if you say cuz. That's not a word. Cuz is not a word. This is class. This is school. You don't say cuz. This ain't the internet. Come on. All right? So say it well. F has a local max. You with me? If you said it a little differently, then run it by me so we can make sure you say it well. Okay. By the same token, say your conclusion. For the other one, F has a local min. Where? At x equal 1 because, oh, that was at -2, wasn't it? Sorry about that. At x equal 1 because time changes from negative to positive. Now, look carefully at my work. On an AP problem, I would not get full credit. What's wrong with my work? Look at the critical point. This is one of the things that very people can't seem to solve. Yeah, they grade for it. Sets the derivative equal to 0. That's the first point on the point. Sets the derivative equal to 0. You could also say 0 / undefined here, but you must, in finding a critical, if you don't show this, you will not get full credit. You're not just finding the derivative. Obviously, with these solutions, it must have been because you were setting it to 0, but that's all in your mind. You didn't write that. So it's important that you use it. Right? Understood? Okay. I'll deal with common mistakes as they come. You guys understand, so this is actually box 3 in a second. But first, let's talk about the extreme value theorem. In Calculus 1, there are 3 existence formulas, existence theorems, excuse me. And they all prove there must be a place where something happens. What is the IDT? The IDT can be used to prove there must be a y value of 2 between these. There must be a place. The mean value theorem is there must be a place where the instantaneous rate of change equals the average rate of change. There must be a place. The extreme value theorem is also there must be a place. It actually has 2 pieces, and in many textbooks they call it part 1 and part 2. The extreme value theorem looks like this. First of all, it deals with absolute extrema, not relative or local extrema. And it goes like this. If a function is continuous on a closed interval, it must have an absolute max and an absolute min. Furthermore, these must be located at an endpoint or a critical number. Now let's talk about this too. First of all, continuous is important because if it's not continuous, then there's the possibility of an asymptote. That definitely doesn't have an absolute max, right? Endpoints are helpful in ensuring, does this guy have an absolute max if it's left to its own devices? No. Does it have an absolute min? It does, but it's not guaranteed to have both unless it is NP. Okay, something like this. Now, once it meets those two conditions, then it must have an absolute max. Now, when I say absolute max, in a proof, you're often not looking for the words absolute max. It's this terrible bit of math speak, something like there exists, which is a backwards E, a C contained in the set A to B such that F at C is greater than or equal to F at all other x's. That's the extreme value theorem in math. Okay. Now, it's important not so much that you read this, but that you know this. There is a y value greater than or equal to all other y values is how you should kind of put that into it. All right? We'll get to that in the next slide. Hang on to that. Number 3, I erased. That stinks. I have that here. Box 3 is this problem key. F of x equals negative x squared plus 3x, and you're given the closed interval 0 to 3. Question is, find the max value of the function on the interval. Okay? Try that. Try it. Try it, say. Try it. And you, oh yeah. How we doing? Okay, so you need critical points first. Make sure you show the grid is set equal to 0 so they know where it's coming from. Did you get 3 halves for a critical point? Okay. Then you're using, rather than do a sign test like the relative extreme of first derivative test, you're just using this idea to shorten it down. The theorem says that the only place an absolute extreme it could be is a critical point or an endpoint, so you really only have to look at 3 places. You don't have to look at over whole intervals. So, based on that, you see who wins the contest, and the contest is won by the max value of All right, so the question then is, what do you cite? Do you say the max value is 3 halves or the max value is 9 fourths? 9 fourths. It says what's the max value when the function, and that's the y value. It doesn't say where is the max, which would be 3 halves. It says what is the max. The max is 9 fourths. If you want to parenthetically say add x equal 3 halves, that's fine, but not necessary. In fact, the extreme value theorem is so powerful that really that is satisfactory. Now, many people then say, good work is to say, because, for example, 9 fourths is greater than 0. My professor, who is from Poland, would always end it by saying, because 9 fourths is the greatest of the candidates, that's fine too. But if you just have that, that's satisfactory. Are you with me? Whatever makes sense to you. Okay, as long as it makes sense to you too. Last but not least, a quick question. This isn't on the homework, but this is a commonly missed AP question. When I say commonly missed AP question, I mean usually only about 30% of the people get it correct on a multiple choice question. So take a look at it and see what you think. So what do you say? 1, 2, 3, 4, or several are true? What? 1, yeah. 1 in plain old English, what does it say? In just your words, what does it mean? It has to have an absolute min. There's got to be a y value less than or equal to all other y values. It must have an absolute min, and that's true because it's continuous on a closed interval. It must have an absolute min. Why not the second one? What does it mean? There has to be a place where crosses the x-axis or y is 0. I don't know that. Why does that have to be true? That's not true. 3, the second one means there must be, obviously, a derivative 0. Graphically, that would mean there's a place where there is a horizontal tangent. That's not necessarily the case either. And does continuity imply differentiability? Not necessarily, no. Differentiability implies continuity. Okay, you follow? All right, that's it. Questions on last night's homework? They asked about 2 on the back in the last class, but that's them. You don't have to ask about 2 on the back. I think they asked about the square root 1 and the proof. So, whatever. Question? Yes? Approve. Okay. I will be happy to. What was the... actually, I have it here. So let me so this is not numbered, sorry, but it's the last problem. This is on homework 6. Last problem, f of x is 3 plus x is less than or equal to 1, x squared plus 3, x is greater than 1, prove the derivative does not exist at x equal 1. Okay, so thank you. Let me tell you what absolutely is not the case. You cannot say, hey, f prime equals 1 and 2x, and hey, looky there, f prime at this, f prime at 1 is 1, but here f prime at 1 is 2, and boom. Let me tell you, this would be about a 3-point question on the AP test, and you would get a 0. Nothing. It's, if you prove the definition of the derivative, or if you prove anything about the derivative, you should be working from the definition of the derivative. This has nothing in the definition of the derivative in that work. So, the question is, Do you want to use the alternate at 1 or the first definition at 1? Either one is fine, but you have to be working specifically at what's going on at 1. I think from experience, most people find the alternate easiest to use. You with me? Okay. Now, the alternate definition says that the derivative at 1 can be found by taking, remember the generic definition looks like this, right? By taking a limit as, in this case, x approaches 1 of f of x minus f at 1 over x minus 1, right? I'm going to kind of just go slowly about this. So, here we go. Well, this is where the problem ensues. I have, you don't need a graph, but to explain this well, I have a line, and the parabola does start at 1, 4. And so the question is, if you take an x on this side and draw the slope, do you get the same as if you take an x on this side and draw the slope with 1? The visual says no, but let's get into the details. If you take an x that is above 1 and approaches 1 from above, then it would look like that. Let's go a little more specific. If I'm going above 1, then what's f of x? X squared plus 3. And what is f at 1? 4, yes? Over x minus 1. This limit is x squared minus 1 over x minus 1. You can see how the x minus 1 would drop out, leaving you with x plus 1. The slope approaches 2. Slope approaches 2. Okay, as it gets closer and closer, the slope starts to approach 2. Cool. If, however, you use an x to the left of 1, then you're looking at approaching 1 from the left. And instead of f of x being x squared plus 3, then you're using f of x is 3 plus x minus f at 1 is still 4 over x minus 1. Well, that gives you x minus 1 over x minus 1, the limit of which is 1, yeah? Now let's give good solid reason. F prime at 1 equals, actually, let's say, no, that's a good way to say this. F prime equals the limit, and the limit doesn't exist. Let's parenthetically say, why doesn't the limit exist? Because 2 is not equal to 1. F prime equals the limit, and the limit doesn't exist. Therefore, the derivative at 1 doesn't exist. The derivative is the limit, and the limit doesn't exist. The derivative cannot exist. If you did the other definition, I can show you that work too. But like I said, I feel like alternate goes better. Okay. Other questions? Yes? Tangent line. Good. Yeah, that one, I probably should have put that in the notes for review, but we'll do it now. The tangent line, to estimate the square root of 11. At the heart of this is the fact that you might say, well, shoot, what's easier to evaluate at 11? That or that? Which one's easier to put 11 into? The line, for sure. Okay, but linear functions are clean. Now, the idea visually is that we have the square root function, boom, and here's 11. And I don't know what it equals when you put it into the square root function. I do know that it's between the square root of 9, which is 3, obviously, and the square root of 16, which is 4. But what? Well, the tangent line idea is to use calculus to make a linear equation at 9. 9 because 9's a nice point on the curve to work with, the one for which I know the y value. That's step 1, find the tangent. Then step 2, instead of plugging 11 into the curve equation, plug 11 into the line equation and see what it equals. And it'll be pretty doggone close to what the curve equals, but it's a lot easier to put 11 into the linear equation. So let's start with step 1, the tangent line. Point, slope, point, slope. What's a point on the tangent line? 9, 3. The slope, how is the slope found? If f of x, if I let f of x equal the square root of x, then the slope is found by f prime at 9, okay? Now, I'm going to show the general derivative in terms of, again, making sure you're safe in terms of earning points. When you do this, you typically show the general derivative, then put in 9, in case they have 2 points built on that in the rubric. Finds the general derivative of any x, then finds it at 9. Show those separately. So, what is the derivative of square root of x? 1 over 2 square roots of x, evaluated at an x of 9 is 1/6. Therefore, my tangent line in point slope form anyway is y minus 3 equals 1/6 x minus 9. All right? Now we're going to use our tangent line to estimate at 11. We know that the linear function is pretty close to the curve at 11, so we're going to put 11 into the line. Y would be 3 plus the 6, I moved the 3 over, of, instead of x minus 9, we put in 11 minus 9. Let's pause here and appreciate the beauty of calculus, shall we? Okay, now, this is magical to me. This is just so cool. Do you agree this is dy dx, yeah? And it says that for every change of 6 units in x, I would expect y to change by 1 unit, right? That's the rate of change here. It's for every 1 y, it's 6x, or vice versa. So that's what this is saying. All right, start at 3, and then change y 1 unit for every x change in x, or 6 change in x. But we're not changing x by 6 units. We're only changing x by 2 units. So because of that, y will only change by, it won't change by a full 1, it'll only change by a third. And so you get 3 1/3, and that's just delicious. All right? So that makes sense. It's a good estimate. What the square root of 11 really is. There's so, if you have so many ways to estimate calculus. You can use methods. Oh, there's so, wow. By the time I'm done with you, you will have almost 11 different approximation methods. I'm so excited for you. 11. I kind of wish I would just forget everything I know just so I could learn calculus all over again. 3.316, so that's pretty doggone close. It's within 200. All right? Does that make sense? Okay. Any other questions? Cool. All right. Have a good, don't have a good day yet. Keep working and then have a good day. Let me know if I can help you. On that homework on tonight, the hardest one by far is the AP problem on the back. So you, it's up to you, of course, but you might try to tackle on that so you can talk it over with your math and English before you leave. But it's, like I said, it's your fault. Let me know if I can help you. Part A is pretty straightforward. B is where it gets tougher. Yeah. Sure.